Hello, my name is Hunter Adamitis, and I'll be showing you my CS142 project. My project was basically about comparing the reduction algorithm in C++17 in comparison to the one created for CUDA in assignment 2. Um, Here, I have I tested this multiple ways. First of all, I've had obviously coded in CUDA to get a reduction algorithm. I created a basic one with little hardware optimization and a more optimized version with that focus on hardware optimization, which is basically meaning I accounted for warp divergences, and so I kept tried to keep all the coalesce the data towards the front of the array to for that purpose. Um, This is my CUDA code, basic stuff. I basically just used the assignment 2 as a template and worked from there. I don't think I need to explain it that much. It's not that thing new. If I use make, I can run both the reduction, the unoptimized reduction algorithm, and the optimized reduction algorithm. And they both gave me times. How I calculated the time from CUDA is I added up the host to device time, the launching the kernel, and then the write back time, because that's how long it took from starting the initial reduction to getting the final result. Um, for my serialized, for my serialized reduction, uh, for my C++ testing, I created a basic reduction algorithm, which basically means I created a for loop and I looped over the addition for basic benchmarking purposes. I can I'll just compile it one more time to make sure it's up to date. Um, Now all it does is all it does is it prints out the result of the addition and the time it took to do so. For my C++ coding, I encountered an issue when it comes to compiling, where basically the GCC embedder was outdated, so I had to find a workaround. So I found this website that does allow me to run the latest version of C++, so that I can actually file code and to account for the variations for like this hardware to other hardware. I ran like simple programs such as adding two numbers, printing hello world, looping through an array at different intervals to see like the finding like was it their multiple indifferences, average that out and multiply that to my final result. Actually put them like one. But basically and this is one of my this is one of my tests to get one of the final results. Here's my actual C++17 code. How it works is it generates an array. It generates an array, and then I have a clock feature that does clock that kind of times from the beginning of it to the end. It prints out the result of the reduction and then the final value. What For a little context, what this reduce function is doing is this par is setting the execution parameter. For par is doing it in parallel. This v1 begin tells it where in the vector to start. we're in the end, and this is the initial value of the function. Now for the last field of the reduce function, you need to include an operation you want to reduce by. And you could do that either two ways. There is a utility that has a lot of binary operations such as multiply, add, and divide. Or you could use a lambda function. I used both in my testing to see if there was any difference. There was. First of all, this is my lambda function. I did all additions and I compared parallelization and sequential processing. And this works, so I will just change this so I can compile. And now it prints out the results. Like I said, it prints out the value, the time it took. And and again, I know this is not how it will work on Bender. So like I said, I found a constant to multiply to all these to kind of estimate of what it would be. Because like I said, Bender cannot use C++ standard 17, and I was not aware of that until too late to fix it. Is there anything else I would like to discuss? Let's see here. Oh, problems I faced was again mostly the Bender issue. The I in combination with my computer dying, I had to kind of scramble like the last couple of days. So it was kind of a struggle to kind of get this coding working. But besides the hardware issues, the coding wasn't all that complicated. C++ 17 is very like it looks confusing at first, but it's kind of readable once you understand what it's trying to say of like what you need to do. And some interesting results I found was that obviously the the GPU was going to be slower than the CPU for like small data sets because again the transfer delay. But what's interesting is that for mediums data, stuff around the millions, 10 million, stuff like that, the reduce function is good at improving performance. Because again, like with the CPU, if you do a serialized in a naive way of just adding through the array, what happens is like the CPU becomes overwhelmed and it just becomes outpaced and you're not at the point where the transfer times are you're not at a large enough data where like the processing speed of parallelization is outweighs the performance hit of the transfer delay. So in that aspect, it's a very useful, but if we go to like some of my data real quick from this. Gosh, but if you go to the data, what you see is actually here that if you implement it incorrectly, you can actually get worse performance. And this was done with a sequential reduction with a binary operation. And on the topic of binary versus lambda, from my limited testing, it appears that as the data set gets higher, the binary operation is not as useful as the what is it as the lambda as lambda function. My guess is due to the fact that the lambda might have better locality because it's written in line, and so it's like so it's accessed more easily. But since it's a utility function, it has to access that function in the library, which has to go through memory, which could potentially hurt performance. Thank you for listening to my presentation. I guess not presentation, but thank you for watching my video.